In 1948, a man who rode a unicycle through the hallways of a telephone company published 79 pages in a corporate journal no physicist would ever pick up. His name was Claude Shannon. He was 32. He thought the paper was totally useless. It turned out to describe the deepest architecture of reality that human beings have ever uncovered. And the physics community ignored it for 50 years because it came from an engineer in the wrong building. Shannon's entropy formula is mathematically identical to Boltzmann's formula for the entropy of the physical universe. Not similar, identical. Physicists noticed they called it a coincidence. It was the biggest clue in the history of science, and nobody followed it. Tonight, we follow it, from Boltzmann's tombstone in Vienna to a glass bead in a laser trap, confirming information is physical. From Shannon and Turing sharing classified tea at Bell Labs in 1943, to a graduate student who gave black holes and entropy written on their surfaces, to the proof that space-time itself is a quantum error-correcting code built on Shannon's principles, and to a nursing home in Massachusetts where the father of information theory was being erased, one synapse at a time, by a disease that destroys information, while physics was finally discovering his equation governs the universe. Get comfortable. If you are not subscribed, hit subscribe. If you want more across physics and the questions nobody follows to the end, the Patreon goes deeper. Stay for this one. What Shannon's equation says about what you are is not something you can unhear. Let's start at the beginning. There are two equations in physics that are identical, not similar, not loosely analogous in the way physicists sometimes gesture at when they are being lazy. Identical. The same mathematical object written in different handwriting. The first was published in 1877 by Ludwig Boltzmann, an Austrian physicist who spent his entire career fighting with the European scientific establishment over whether atoms were real. He suffered from depression. He was mocked by the positivist philosophers who dominated physics at the time, men like Ernst Mach, who believed that atoms were a useful fiction and that Boltzmann was wasting his life chasing phantoms. In 1906, during a family vacation in Duino, Italy, while his wife and daughter were at the beach, Boltzmann hanged himself. He was 62. His tombstone in Vienna is engraved with his entropy formula, S equals K log W. The equation survived him. The equation was correct, the atoms were real. And one specific version of that equation, a more general formulation, written as S equals negative K sub B sigma P sub I ln P sub I, would turn out to be the most important equation in physics that nobody recognized for what it was. The second equation was written 71 years later, in 1948, by a man who rode a unicycle through the corridors of a telephone company while juggling 3 balls in the air. His name was Claude Shannon. His equation looked like this: H equals negative sigma P sub I log 2 P sub I. He published it in a corporate engineering journal, the Bell System Technical Journal, a publication no physicist would ever pick up voluntarily. Boltzmann's equation describes the entropy of a physical system, the disorder of gas molecules, the tendency of the universe to slide from structure into chaos. It governs the behavior of stars, the flow of heat, the arrow of time, the eventual death of everything. Shannon's equation describes the entropy of a message, the uncertainty, how many binary questions, how many yes or no choices you would need to pin down which message was sent. It governs how efficiently you can compress a file, send a text, stream a video. One is about the physics of the cosmos. The other is about communication engineering. They have nothing to do with each other. They should have nothing to do with each other. And they are mathematically the same equation. The physics community looked at this for almost 50 years and called it a coincidence. It was not a coincidence. It was the biggest clue in the history of science, sitting in plain sight. And the people whose job it was to follow clues walked past it for half a century. And the reason they walked past it tells you something deeply disturbing about how science actually works, about what happens when the right answer shows up in the wrong building. The man who wrote the second equation was Claude Shannon, born April 30th, 1916, in Petoskey, Michigan. Raised in the small town of Gaylord, where his father was a probate judge and his mother was a school principal. He was a distant cousin of Thomas Edison, which sounds like something a biographer would invent for narrative convenience, but it is documented fact. As a teenager, he built a telegraph system between his house and a friend's house half a mile away, stringing it along barbed wire fencing. He worked as a Western Union messenger boy. He took things apart. He put them back together. He wanted to know how everything worked underneath. And he had the sort of mind that could look at two completely different systems and see the same hidden pattern running through both of them. This quality, this ability to spot deep structural identity where everyone else saw unrelated surface features, would define his entire career. He earned 2 bachelor's degrees from the University of Michigan in 1936, one in mathematics and one in electrical engineering, and then went to MIT as a research assistant to Vannevar Bush. Bush was the most powerful science administrator in America, the man who would later direct the Office of Scientific Research and Development during the war and write the famous report, Science, the Endless Frontier, that created the post-war American research system. But in 1936, Bush was an engineer, and he had built a machine called the differential analyzer, a room-sized mechanical computer that could solve differential equations using rotating shafts and metal gears and a terrifying web of electrical relay circuits. Shannon's job was to operate it, to crawl around inside this enormous apparatus, to trace the wiring, to understand how the relay circuits actually worked and how to configure them for each new problem. And inside that machine, Shannon saw something that nobody else had seen. He realized that the on-off states of an electrical relay, open circuit or closed circuit, were mathematically identical to the true-false values of Boolean algebra. George Boole, a self-taught English mathematician, had published his Algebra of Logic in 1854. It was an abstract symbolic system for reasoning about propositions, true or false, and Oregon not. Engineers had been building electrical relay circuits for decades. The two fields existed in separate intellectual universes. Nobody had connected them. Shannon connected them. His master's thesis, submitted in 1937, entitled A Symbolic Analysis of Relay and Switching Circuits, proved that any logical or arithmetic operation could be implemented with a properly designed network of electrical switches. This was the founding insight of digital circuit design, the bridge between abstract logic and physical machinery. Howard Gardner has called it possibly the most important and most noted master's thesis of the 20th century. Every microprocessor manufactured since, every chip in every device you have ever used, traces its lineage to that document. Shannon was 21 years old when he wrote it. He was not trying to change the world. He was trying to graduate. His PhD thesis at MIT, completed in 1940, was titled An Algebra for Theoretical Genetics. It was a perfectly competent piece of work, and it was almost entirely forgotten. Shannon's genius was specific. It fired when he saw hidden structural identities, when he found the same abstract pattern in two systems that nobody else thought were related: Boolean logic and electrical circuits, thermodynamic entropy and information uncertainty. He was a pattern-matching machine of extraordinary power, and his patterns kept turning out to be the ones that mattered most. After a year at the Institute for Advanced Study in Princeton, on a National Research Fellowship, where he interacted with Hermann Weyl and John von Neumann, Shannon joined Bell Telephone Laboratories in 1941, and here the story splits into two timelines that ran in parallel, both classified, both world-changing, both featuring men who would have been legendary on the strength of either one alone. The first timeline is cryptography. Shannon was assigned to wartime work on fire control systems and on the mathematics of secrecy. He worked on the X-2 anti-aircraft predictor, a system used to shoot down V-1 buzz bombs over London, and he worked on the theoretical foundations of cryptography, producing a classified memorandum dated September 1st, 1945, titled A Mathematical Theory of Cryptography. This was declassified and published in 1949 as Communication Theory of Secrecy Systems in the Bell System Technical Journal. It laid the mathematical groundwork for modern cryptography. Shannon himself said later that the theory of secrecy and the theory of communication were so close together you could not separate them. They were the same problem turned inside out. Hiding a message and transmitting a message were mirror images of each other, and the mathematics that governed one governed the other. The second timeline involves Alan Turing. In January of 1943, the British cryptanalyst was sent to Bell Labs to share intelligence about Bletchley Park's methods for breaking the German naval enigma, and to advise on Sig Sally, the first digitally encrypted voice telephone system which was being used for secure conversations between Roosevelt and Churchill. According to Andrew Hodges' biography of Turing, Shannon and Turing met daily for tea in the Bell Labs cafeteria. During this period, both men were sitting on top of classified work that they could not discuss with each other. Shannon had his cryptography research. Turing had Enigma. So instead of talking about what they were actually working on, they talked about something else entirely. They talked about machines that could think. Turing had published his paper on computable numbers in 1936, defining the universal machine. Shannon was already developing ideas about information and computation that would eventually become his 1948 paper and his 1950 paper on chess-playing programs. Two of the most important minds of the 20th century, sitting in a cafeteria, forbidden from discussing their most important work, instead laying the intellectual groundwork for artificial intelligence over tea. Shannon later recalled that Turing did not always agree with his ideas. He didn't always believe these, my ideas, Shannon said. He didn't believe they were in the right direction. History would settle who was pointed in the right direction, and it was not the direction Turing expected. There is another side of Shannon that matters for this story, and it is the side that proves he understood, even then, that information was not abstract. Shannon, the man who would prove that information has mathematical structure and physical consequences, also understood that information has economic consequences. In the late 1950s, his Bell Labs colleague, John L. Kelly Jr., published a new interpretation of information rate, which used Shannon's information theory to derive the optimal strategy for sizing bets. The Kelly criterion: bet a fraction of your capital equal to your edge, divided by the odds, maximizing the expected logarithmic growth of your wealth. Shannon took this very seriously. In 1960, he received a manuscript from a young MIT mathematician named Edward Thorpe. who had developed a mathematical system for beating the game of blackjack. Shannon and Thorpe became collaborators and friends. Together, in Shannon's basement laboratory, they built the first wearable computer in history. It was the size of a cigarette pack, contained 12 transistors, and was designed to beat roulette. The device timed the velocity of the roulette ball and the rotor using toe-operated microswitches, computed the probable landing zone, and transmitted the prediction to a receiver hidden in the bettor's ear. Thorpe later wrote, in a 1998 paper for the Proceedings of the Second International Symposium on Wearable Computers, that the final operating version, tested in Shannon's basement in June of 1961, yielded an expected gain of plus 44% when betting on the most favored octant. The Shannons and the Thorpes went to Las Vegas in the summer of 1961. A speaker wire kept breaking, preventing sustained play, and they never deployed the system for serious money. But Shannon applied information theory to the stock market with devastating effectiveness. He held a concentrated portfolio heavily weighted toward Teledyne, Motorola, and Hewlett-Packard, and achieved annualized returns of roughly 28% from the late 1950s through 1986, according to William Poundstone's book, Fortune's Formula. A Barron's survey on August 11th, 1986 found that Shannon had outperformed 1,025 of 1,026 tracked mutual funds. The man who proved information could be measured also proved it could be monetized. He and Betty lived in a house they called Entropy House. He was, in every sense, a person who understood that information was not just an idea. It was a thing in the world, with real consequences, all of which makes it that much more important that you understand what happened when he finally published the paper that everyone remembers, and almost nobody actually read. The paper was titled A Mathematical Theory of Communication. Note that title carefully. A, not the. Shannon chose the indefinite article deliberately, modestly, as if to say this was merely one possible approach. It was published in 2 parts in the Bell System Technical Journal, Volume 27. Part 1 appeared in the July 1948 issue, pages 379 through 423. Part 2 appeared in October, pages 623 through 656. 79 pages in total. According to Sophia Rare Books, Shannon had not initially planned to publish the paper at all, and only did so at the urging of colleagues. The most consequential 79 pages of the 20th century almost remained a set of notes in a desk drawer. Shannon opened the paper with what is now the canonical diagram of any communication system. An information source produces a message. A transmitter encodes the message into a signal. The signal passes through a channel that adds noise. A receiver decodes the corrupted signal. A destination gets the reconstructed message. 5 boxes and a squiggly line labeled noise. That diagram, simple as it looks, contained the entire conceptual framework for every digital communication system built since. Every phone call, every email, every streamed video, every packet of data, they all pass through Shannon's 5 boxes. But the diagram was just the framework. The substance was in the theorems, and to prove those theorems, Shannon needed to do something unprecedented. He needed to define information in mathematical terms, not meaning. Shannon was explicit, almost defensive, on this point. The semantic aspects of communication, he wrote, are irrelevant to the engineering problem. He did not care whether a message was true or false, profound or trivial, beautiful or ugly. He cared about one thing only. How surprising is it How many binary choices does the receiver need to make in order to determine which message was sent from among all possible messages? A message that tells you something you already know is entirely predictable. It carries zero information. A message that is completely unpredictable, that could equally be anything, carries maximum information. Information, in Shannon's framework, is resolved uncertainty. And the formula he derived for the total uncertainty of a source, the entropy, was H equals negative sigma p sub I log 2 p sub I, where p sub I is the probability of the ith possible message. It was John Tukey, Shannon's colleague at Bell Labs, who suggested the word bit for the base 2 unit. Tukey had coined it in an internal memorandum dated January 9th, 1947. Binary, digit, bit. That word, born as a casual contraction in a Bell Labs memo, would become one of the most important words in the English language. But the naming of the formula, important as it became for the history of physics, is not the part of the paper that matters most. What matters is what Shannon did with his formula. Because once he had a way to measure information, he could ask the questions that nobody had been able to formalize before. How much can you compress a message without losing anything? How fast can you send a message through a noisy channel without it getting garbled? Is there a fundamental limit to the reliability of communication? And the answers he got, the theorems he proved, were not just useful for engineers. They turned out to be statements about the structure of reality that are as inviolable as the conservation of energy. To understand what Shannon proved, you need to appreciate how radical the claims sounded in 1948. Engineers in that era treated noise as a practical nuisance to be minimized through better hardware. They thought of information as something you push through a wire, like water through a pipe, and noise was the friction. Better pipes, less friction, cleaner signal. Shannon showed that this way of thinking was completely wrong. Noise is not friction. Noise is a fundamental feature of any physical channel. It cannot be eliminated, but it can be beaten. And the way to beat it is not through better hardware, but through better mathematics, through encoding. Consider what this means. Shannon was saying that the laws of information impose hard limits on communication, the same way the laws of thermodynamics impose hard limits on engines. A heat engine cannot convert more than a certain fraction of thermal energy into work, no matter how cleverly it is designed. Shannon was claiming an analogous result for information. There is a maximum rate at which a channel can carry reliable information, determined by the channel's physical properties, and no encoding, no matter how clever, can exceed it. But any rate below the maximum can be achieved with essentially perfect reliability if you use the right code. This was the conceptual revolution. Not that limits exist, but that the limits can be approached. That there exist codes good enough to transmit information reliably at rates approaching the fundamental capacity through channels corrupted by arbitrary amounts of noise. Shannon did not just identify a ceiling. He proved the ceiling is achievable, and that proof changed the nature of engineering from an art of compromise into a science of optimization with a known target. Shannon then proved two theorems that engineers spent the next 70 years absorbing, and that physicists are only now beginning to understand the full implications of. The source coding theorem proved that if you have a source of messages with entropy h bits per symbol, you can compress those messages to an average of h bits per symbol, but you cannot do better. This is the hard mathematical flaw beneath every compression algorithm ever written. Zip, JPEG, MP3, the lossless and lossy codecs that make the modern internet possible. They are all approaches to the Shannon limit. Approaches, not violations. The limit cannot be broken. It is not an engineering challenge. It is a mathematical law as inviolable as the conservation of energy. The noisy channel coding theorem proved something that sounded, when Shannon stated it, like it should be impossible. It proved that for any noisy channel, there exists a maximum rate C, the channel capacity, below which you can transmit information with an error rate as close to zero as you wish, not acceptably small, as close to zero as you wish. Arbitrarily reliable communication at any rate below C, and impossible communication above it. For a channel with bandwidth bHz and signal-to-noise ratio S/n, the capacity is C equals B log 2 of 1 plus S/n bits per second. This is the Shannon-Hartley theorem. It explains why your dial-up modem in the late 1990s could never quite break 56 kilobits per second. A 4 kHz telephone line with roughly 20 decibels of signal-to-noise ratio has a Shannon capacity of about 26.6 kilobits per second. That number is a wall. It was placed there by mathematics. No engineering cleverness can move it. But the noisy channel coding theorem proved something else, something deeper, something that went unrecognized for decades. It proved that error correction is achievable, that there exist coding schemes capable of transmitting information through any noisy channel at rates approaching the capacity limit with vanishingly small error. Shannon proved these codes exist. He did not build them. He proved their existence as a mathematical certainty and left it to future generations to find them. Engineers spent 60 years on the search. Richard Hamming at Bell Labs in 1950, Irving Reed and Gustav Solomon at MIT Lincoln Laboratory in 1960, Robert Gallagher and his low-density parity check codes in 1963, Claude Barrow's turbo codes in 1993, which came within a fraction of a decibel of the Shannon limit, Erdal Arikan's polar codes in 2009, the first provably capacity-achieving codes with practical encoding complexity, which was subsequently chosen for use in 5G cellular networks. Each generation confirmed what Shannon had said in 1948. The codes are out there. The limit is real. The mathematics does not lie. And then, in 2015, a group of physicists discovered that the universe itself appears to be using one of these codes, that the very fabric of spacetime is structured as a quantum error-correcting code, protecting information from destruction, using principles that are, at their mathematical core, the same principles Shannon described in a telephone journal. But here is something about Shannon's theorems that rarely gets discussed, and it is the detail that connects the engineering to the physics. Shannon proved that error-correcting codes exist. He proved they can approach the channel capacity. But he also proved something about the nature of optimal codes that sounds abstract until you realize what it implies about the physical world. Optimal codes are random. Or rather, they look random. The best error-correcting codes distribute information across the encoded message in a way that makes every part of the encoded signal look like noise to anyone who does not have the decoding key. The signal and the noise become statistically indistinguishable. This is not an engineering trick. This is a mathematical necessity. It is the only way to use the channel capacity fully. Now think about what that means for a universe that is, at its most fundamental level, running Shannon's algorithm. If spacetime is an error-correcting code, and optimal error-correcting codes make the encoded information look random, then the apparent randomness of quantum mechanics might not be randomness at all. It might be optimal encoding, the noise of the quantum world, the irreducible uncertainty that Heisenberg discovered and that has confused physicists for a century, might be the signature of an error-correcting code operating at the deepest level of reality. I want to be clear that this is my interpretation and not an established result. But the mathematical structure is suggestive in a way that is very hard to dismiss. There is another connection that I think is underappreciated. Shannon's source coding theorem says that you cannot compress a message below its entropy without losing information. His channel coding theorem says that you can protect information from noise up to the channel capacity. Between them, these two theorems define the complete landscape of what you can and cannot do with information in the presence of physical constraints. And that landscape is not just relevant to telephone wires, it is relevant to biology. DNA is a digital code. It uses 4 bases: adenine, thymine, guanine, cytosine, to encode information in sequences that are read, copied, and executed by molecular machinery. The genome of a human being contains approximately 3.2 billion base pairs, encoding roughly 750 megabytes of information. And the cellular machinery that copies DNA polymerase, makes errors at a rate of roughly 1 in 10 billion base pairs per replication cycle, after error correction by proofreading and mismatch repair enzymes. That error rate is not accidental. It is the result of billions of years of natural selection, optimizing an error-correcting code within the constraints of chemistry and thermodynamics. Shannon's theorems describe the limits of what that optimization can achieve. The genome is not just a code. It is a code operating near the Shannon limit of its biochemical channel, and it has been approaching that limit for 3.8 billion years. Shannon did not know this. He did not even think about biology when he wrote the paper. But his theorems are universal. They apply to any system that stores, transmits, or processes information, regardless of whether the system is made of copper wires, silicon transistors, glass beads in laser traps, or nucleotide sequences in a cell nucleus. The laws of information do not care about the substrate. They care about the mathematics, and the mathematics is the same everywhere. But that discovery required a chain of insights stretching over 100 years, and the first link in that chain was forged not by Shannon, but by a Scottish physicist and a hypothetical demon. In 1867, James Clerk Maxwell, who had already unified electricity and magnetism into a single framework, proposed a thought experiment designed to test the absolute limits of the second law of thermodynamics. The second law says entropy always increases. Heat flows from hot to cold, never the reverse. Order degrades into disorder. Time moves forward. These are not suggestions. They are the most fundamental asymmetry in order physics. Maxwell wanted to know if there was a loophole. His thought experiment went like this. Take a box of gas at uniform temperature. All the molecules are bouncing around randomly. Thermal equilibrium. Maximum entropy for this configuration. Now put a partition through the middle with a tiny trapdoor and station a very small, very intelligent being at the door. Lord Kelvin later named this being Maxwell's demon. The demon can see individual molecules. When a fast molecule approaches from the left, the demon opens the trapdoor and lets it pass to the right. When a slow molecule approaches from the right, the demon lets it pass to the left. All others are ignored. After enough time, the fast molecules are concentrated on one side and the slow molecules on the other. One half of the box is hot. The other is cold. A temperature difference has been created from a uniform state, which means usable energy has been generated from nowhere. An engine could run on this difference. The demon appears to have decreased entropy, creating order from chaos without doing any work. The second law appears to be violated by cleverness. This bothered physicists for a very long time. Over 60 years, in fact. The thought experiment was not a frivolous puzzle. If the second law has a loophole, then perpetual motion is possible. Energy can be created from nothing, and the arrow of time is negotiable. These are not small stakes. The second law of thermodynamics is, in the famous words of Arthur Eddington, the supreme law of nature, the one law that if your theory disagrees with it, your theory is wrong. Leo Szilard, a Hungarian physicist who would later help initiate the Manhattan Project, published a paper in 1929 titled On the Decrease of Entropy in a Thermodynamic System by the Intervention of Intelligent Beings. Szilard analyzed a simplified version of Maxwell's demon, a single-molecule engine, and argued that the demon's act of measurement, of learning which side the molecule is on, must generate enough entropy to compensate for the decrease. The second law is saved because acquiring information has a thermodynamic cost. Szilard was pointing in the right direction. But his analysis was not precise enough to close the case. The question of exactly where the thermodynamic cost enters and exactly how large it is remained open for another 32 years. And when the answer finally came, it came from the IBM research lab in Yorktown Heights, New York, from a physicist named Rolf Landauer. In 1961, Landauer published a paper in the IBM Journal of Research and Development titled Irreversibility and Heat Generation in the Computing Process. The paper is one of the most underappreciated documents in the history of physics. What Landauer proved was surgically precise. He showed that measurement is not the operation that costs entropy. Copying is not the operation that costs entropy. The only operation that is necessarily and unavoidably irreversible is erasure, the destruction of information. Every time one bit of information is erased, irreversibly, a minimum of K sub B times T times ln2 of energy must be dissipated as heat into the environment. At room temperature 300 Kelvin. This works out to approximately 2.87 times 10 to the minus 21 joules per bit. To put that in perspective, the kinetic energy of a single oxygen molecule at room temperature is about 6 times 10 to the minus 21 joules. Landauer's limit says that erasing one bit costs about half the energy of one molecule bouncing off a wall. A single raindrop carries about 1,000,000 trillion times more energy. Your laptop dissipates roughly 100,000 times more heat per bit than the Landauer minimum. The number is tiny, but it is not zero, and its existence transforms the nature of information. This is where I need to correct a misconception that has been repeated so many times that even scientists get it wrong. The common narrative says Maxwell's demon is defeated because measurement requires energy. That is Szilard's original argument, and Charles Bennett at IBM showed in 1982 that it is incorrect. Bennett demonstrated that measurement can be performed reversibly, thermodynamically, for free. You can learn which side of the speed distribution a molecule falls on without paying any entropy cost whatsoever. The cost comes later. The demon must record the measurement result. Its memory fills up, and to continue operating, it must eventually erase old measurements to free memory. That erasure is where the Landauer cost kicks in. That is where entropy is generated. The demon is not defeated by the act of knowing. It is defeated by the act of forgetting. The implications of this are profound, and they have not been adequately communicated to anyone outside a small circle of physicists and information theorists. The universe does not charge you for learning something. It charges you for losing it. The thermodynamic cost, the irreversibility, the entropy generation that drives the second law and gives time its direction, is attached to the destruction of information, not its creation. This means that the arrow of time, the most fundamental asymmetry in all of physics, is an informational phenomenon. Time moves forward because information is being erased. Entropy increases because the universe is forgetting, and every act of forgetting has a minimum cost, denominated in heat, calculable to arbitrary precision using Shannon's mathematics. I want to spend a moment on what this means for computing, because it connects to something that will matter later when we get to black holes. Every computer you have ever used is a machine for processing information. And processing information means, at some point, erasing old states to make room for new ones. Every time your processor clears a register, every time your RAM is overwritten, every time a cache line is flushed, the Landauer tax is paid. As of 2025, the most advanced processors dissipate somewhere around 10,000 to 100,000 times the Landauer minimum per logic operation. That gap has been shrinking decade by decade as transistors get smaller and more efficient. The question is, what happens when the gap closes? What happens when computing technology actually approaches the Landauer limit? The answer is that you hit a wall. Not an engineering wall, a physics wall. A wall as fundamental as the speed of light. A wall that says you cannot process information without generating heat. And the minimum heat per bit erased is set by the temperature of your environment and the value of Boltzmann's constant. This means that the energy cost of computation has a thermodynamic floor. And that floor is set by Shannon's entropy formula, operating through Landauer's principle. If you wanted to run a computer at room temperature that erased 1 bit per second, the absolute minimum power consumption would be about 2.87 times 10 to the minus 21 watts. Multiply by 10 to the 18 for a modern processor erasing a billion bits per second, and you get a few milliwatts. Current processors use tens of watts. The gap is real, and it is closing. But here is where it gets strange. The Landauer limit applies everywhere, not just to silicon chips. It applies to any physical process that erases information. It applies to the evaporation of a droplet, because the specific arrangement of molecules in the droplet is information, and when the droplet evaporates, that information is dispersed. It applies to the weathering of a rock, because the specific structure of the rock's surface is information, and erosion erases it. It applies to the cooling of a star, because the specific configuration of a plasma is information, and cooling changes it irreversibly. Every irreversible process in the universe is, in the Landauer framework, an act of information erasure, and every one of them generates at least K sub b TLN2 per bit of heat. This is what Landauer meant when he said information is physical. He did not mean it metaphorically. He did not mean that information is like a physical quantity. He meant that information is a physical quantity in exactly the same way that energy is a physical quantity. It is conserved by the fundamental equations. It has thermodynamic consequences. It participates in the laws that govern the behavior of every system in the universe, from subatomic particles to galaxy clusters. And the physics community ignored this for decades because it was published by an engineer in the wrong journal. Landauer spent 30 years saying this. He published paper after paper at IBM insisting that information is not a metaphor for something physical. It is physical. It has thermodynamic weight. It participates in the laws that govern the universe. And for 30 years, the response from the broader physics community ranged from polite indifference to active dismissal. In 1991, Landauer published an essay in Physics Today, Volume 44, Number 5, pages 23 through 29. He titled it, "Information is Physical." The title was a scientific claim and a 3-word rebuke of 43 years of institutional neglect. He wrote that computation is inevitably performed with real physical degrees of freedom, obeying the laws of physics, and that the information processing character of physical law is something we need to take seriously. This was 1991, 43 years after Shannon's paper, 30 years after Landauer's own proof, and the physics community was only just beginning to listen. Landauer died in April of 1999. He was 71. He did not live to see his principle experimentally confirmed in a laboratory. That confirmation came 13 years later, and it is one of the cleanest, most decisive experimental results in modern physics. In 2012, Antoine Berru, Artak Arakelian, Artyom Petrosyan, and Sergio Kiliberto at the Laboratoire de Physique at ENS Lyon, with Raoul Dillenschneider and Eric Lutz of the University of Kaiserslautern and later Augsburg, published their result in Nature, volume 483, pages 187 through 189. March 8, 2012. Experimental verification of Landauer's principle linking information and thermodynamics. The experimental setup was beautiful in its simplicity. They trapped a single colloidal silica bead, a glass microsphere roughly 2 micrometers in diameter, in a double well potential created by 2 focused laser beams. The 2 wells represented 2 stable positions. Bead in the left well is a 0. Bead in the right well is a 1. This is a 1-bit memory, not a computer, not an engineered information processing device. A glass ball in water, held in place by light. The simplest possible physical system that can store 1 bit. To erase the bit, the experimenters tilted the potential by adjusting the laser intensities, gradually lowering the barrier between the wells and forcing the bead into one specific well, regardless of its starting position. They measured the heat dissipated into the surrounding water during this process, averaging over many thousands of erasure cycles at different speeds. The result was unambiguous. In the slow cycle limit, as the erasure was performed more and more gradually, the mean dissipated heat converged to K sub B TLN 2. Landauer's limit, the minimum thermodynamic cost of destroying 1 bit of information, measured in a real physical system 51 years after it was predicted, matching the prediction with an experimental precision. I want you to understand what was proved in that laboratory. A glass bead in a pool of water, held by laser light, was forced to forget which well it had been sitting in, and the universe extracted a thermodynamic toll for that forgetting. The bead did not know it was storing information. The water did not know it was acting as a thermal reservoir. The lasers did not know they were writing and erasing bits. None of the components had any awareness of the information theoretic framework they were participating in. And yet, the universe enforced Landauer's limit with the same precision it enforces the conservation of energy or the constancy of the speed of light. The same equation Shannon wrote in a telephone journal in 1948, combined with Landauer's insight about erasure, predicted the exact amount of heat generated by a glass ball forgetting its position in a pool of water. Information is physical. It was always physical. The equation Shannon published in 1948 was never about phone calls. It was about the universe. And the universe does not wait for physicists to agree before it enforces its own laws. And here is the part that I have been building toward. The thread I need you to hold because it connects everything at the end. If information is physical, if the destruction of information has a thermodynamic cost that the universe enforces at the molecular level without exception, then the information stored in your brain is physical. Your memories are not floating in some abstract space, disconnected from the material world. They are encoded in the electrochemical states of roughly 86 billion neurons, the strengths of approximately 100 trillion synaptic connections, the concentrations of neurotransmitters in vesicles smaller than the wavelength of light. That encoding is information, real, measurable, Shannon quantifiable, Landauer-bound information. And when it is erased, whether by the normal process of forgetting, by traumatic brain injury, by neurodegeneration, by death, the universe collects its tax. Every memory you have ever lost released heat. An undetectably small amount of heat, yes, but calculable, mandated, written into the same laws that govern the erasure of a glass bead in a laser trap. Shannon's equation does not discriminate between a phone call, a glass bead, and the memory of your daughter's face. The mathematics is the same. The thermodynamics is the same. But the Landauer limit, the physical reality of information, the resolution of Maxwell's demon, all of that is not the end of this story. It is the midpoint, because the truly disturbing results begin when you follow Shannon's mathematics into the most extreme physical environments in the universe and discover that information is not just real, it is indestructible. That the universe does not merely account for information, it refuses to lose it, and that refusal turns out to reshape everything we thought we understood about space, time, and what you are. There is a document you should know about. It is 1 page long. It was published in March of 1956 in the IRE Transactions on Information Theory, volume IT2, number 1, page 3. It is titled The Bandwagon. Claude Shannon wrote it, and I think it is one of the most important and most overlooked documents in the history of science. Not for what it says about information theory, but for what it reveals about how science actually works when it encounters a truth it is not ready for. Shannon, 8 years after his masterpiece, sat down and wrote a formal editorial warning the scientific community that they were simultaneously overusing and underusing his ideas. On one side, researchers in biology, psychology, linguistics, economics, and a dozen other fields had grabbed information theory and started applying it to everything. They were publishing papers with titles like Information Theory and Music, and Information Theory and the Organization of Living Systems, and Application of Information Theory to Economic Analysis. Most of these applications were superficial. They borrowed the vocabulary of information theory without engaging with its mathematics. Shannon called them out. He wrote that information theory had been ballooned to an importance beyond its actual accomplishments. But here is what nobody talks about when they cite the bandwagon editorial. The overuse was happening in the fields where Shannon's theory did not naturally apply. And the underuse was happening in the one field where it did. Physics, where the entropy formula was identical, where the mathematical identity between uncertainty in a message and disorder in a physical system was not analogous but exact, where the connection, if taken seriously, would force a complete rethinking of what entropy actually is, what the second law actually means, and what role information plays in the deep structure of reality. The physicists were not reading Shannon. They were not reading the Bell System Technical Journal. They were not engaging with a paper published by an engineer at a telephone company, because they assumed, with the specific brand of institutional arrogance that pervades academic science, that nothing published in a corporate journal by a non-physicist could contain anything fundamental about physics. A few people tried to build the bridge. Léon Brillouin, a French-American physicist who had done important work on solid-state physics and quantum theory, published Science and Information Theory in 1956. It was an entire book dedicated to making the case that Shannon entropy and thermodynamic entropy were the same quantity, that Maxwell's demon is an information processing agent, and that physics needed to take the information theoretic perspective seriously. The book was reviewed, cited occasionally, and largely set aside by the mainstream. Brillouin was treated as a competent physicist with an interesting but ultimately peripheral hobby horse. He never achieved the recognition his insight deserved. E.T. Jaynes, a physicist at Washington University in St. Louis, published 2 papers in 1957 in Physical Review that reformulated the foundations of statistical mechanics entirely in terms of Shannon entropy. His argument was elegant and radical. He said the probability distributions used in statistical mechanics are not objective features of physical systems. They are expressions of our ignorance. The maximum entropy formalism, choosing the probability distribution that maximizes Shannon entropy, subject to the known constraints, is not a physical principle. It is a principle of inference. It is the correct way to reason when you have incomplete information about a system. And the fact that it reproduces all of thermodynamics is telling you something about what thermodynamics actually is. Jaynes was right. His framework is now the foundation of Bayesian statistical mechanics and has found applications across physics, machine learning, and signal processing. But in the 1950s and 60s, he was treated as a philosopher with interesting ideas, not as a physicist with a correct theory. The mainstream continued to treat Shannon entropy as an engineering tool and Boltzmann entropy as physics, and the fact that they were the same equation continued to be filed under coincidence. And here is where I need to name something that the polite versions of the story always leave out. The reason the physics community ignored Shannon was not primarily intellectual. It was sociological. Physics in the mid-20th century was organized around a hierarchy of prestige. At the top sat particle physics and general relativity. Below them, quantum mechanics and nuclear physics. Below them, solid-state physics and statistical mechanics. And far below all of these, barely visible, sat engineering. Shannon was an engineer. He worked at a telephone company. His paper appeared in a corporate technical journal, and the implicit, unspoken assumption of mid-century physics was that fundamental truths about the universe emerge from places like Princeton and Cambridge, and CERN, not from the research division of AT&T. This assumption was wrong. It was catastrophically, embarrassingly, provably wrong. And the cost of being wrong was measured in decades during which the connection between information and thermodynamics went unexplored. Decades during which Maxwell's demon remained only partially exercised. Decades during which black hole thermodynamics would have to be rediscovered from scratch by physicists who did not realize that Shannon had already given them the mathematical vocabulary they needed. I think about this a lot. I think about what would have happened if a single prominent physicist in 1949 had picked up the Bell System Technical Journal, read Shannon's paper, noticed the entropy formula, and said publicly that this demands investigation. If Bohr or Dirac or Pauli had said the words, Shannon's information entropy appears to be identical to Boltzmann's thermodynamic entropy, and this identity requires an explanation, the entire trajectory of 20th century physics might have been different. The information paradigm might have arrived 30 or 40 years earlier. Bekenstein might have had the conceptual framework in place when he was an undergraduate, rather than having to build it himself as a graduate student. The information paradox might have been posed and partially resolved before Hawking radiation was even discovered. We will never know, but the delay was real, and its cause was not a failure of evidence, but a failure of attention driven by institutional prejudice about where important ideas are allowed to come from. And Landauer, of course. Landauer at IBM, publishing his 1961 paper, then spending the next 3 decades arguing that information is physical, that erasure costs energy, that the second law of thermodynamics is fundamentally about information processing. He was not ignored exactly. His paper was cited. His result was known. But it was known the way a piece of furniture is known. People walked around it. They acknowledged its existence without letting it change anything about how they thought about physics. The cost of this delay is hard to overstate. Between 1948 and 1991, 43 years of physics research proceeded without fully recognizing that information is a physical quantity, that Shannon's framework describes something real about the universe, that the matching entropy formulas were a clue that demanded investigation. Imagine if the connection had been taken seriously in the 1950s. Imagine if physicists had followed the Shannon-Boltzmann identity to its logical conclusion when the evidence was already sitting there in matching equations. The entire trajectory of modern physics might have been accelerated by decades. The information paradox, the holographic principle, the error-correcting structure of spacetime. These discoveries might have arrived a generation earlier. Instead, the paper sat in a telephone journal. The engineer sat in his office at Bell Labs, then in his house called Entropy House, building gadgets and riding unicycles and investing in Teledyne stock. And the physics community conducted what might be the longest accidental experiment in scientific history, an experiment in how long the most important result of the century can sit in plain sight before someone picks it up. There is a painful coda to the institutional failure, and it involves Shannon's own body. The Alzheimer's diagnosis came in the late 1980s. Precisely when is not publicly documented. But by the early 1990s, it was clear to his family and colleagues that something was deeply wrong. Shannon, the man who had spent his career studying how information moves through noisy channels and whether it can be preserved against corruption, was watching his own channel degrade, his own error correction failing, the noise overtaking the signal. The timing of the diagnosis carries its own cruel symmetry. In the late 1980s, precisely when Shannon's mind began its decline, the physics community was finally beginning to take the information physics connection seriously. Landauer's 1991 essay would catalyze the conversation. The holographic principle would emerge in 1993. The field was waking up, and the man whose work had started it all was falling asleep. Consider the parallel timelines. In 1993, 't Hooft proposed the holographic principle, arguing that the maximum information content of space scales with surface area. In that same year, Shannon entered full-time residential care. In 1995, Susskind formalized the holographic principle, completing the generalization of Bekenstein's bound. Shannon could no longer feed himself. In 1997, Maldacena published ADS/CFT, the most important paper in modern theoretical physics, demonstrating that spacetime itself is holographic. In that same year, Hawking and Thorne bet Preskill and Encyclopedia on the fate of information in black holes. Shannon did not know what an encyclopedia was anymore. The physics community was discovering that Shannon's equation describes the architecture of reality. And Shannon was in a nursing home in Massachusetts, unable to recognize his wife. Betty Shannon, who had married him in 1949, who had been his intellectual partner for 4 decades, who had lived with him in Entropy House and raised their 3 children, watched all of this. She told reporters that in his final years, Claude was not aware of how his work had changed the world. He did not understand that the equation he had written had built the internet, powered the mobile phone revolution, and laid the groundwork for a reconceptualization of reality itself. He lived in a nursing home in Medford, Massachusetts. His brain, the organ that had produced two of the most important insights of the 20th century, the bridge between logic and circuits, and the bridge between information and entropy, was being systematically dismantled by a disease that operates by destroying information, by erasing synaptic connections, by degrading the physical substrate in which Shannon's own memories were encoded. Every memory he lost was a Landauer event. Every synaptic connection that degraded released its tiny tax of heat into the room. The math is exact. The same equation Shannon published in 1948 predicts, with the addition of Landauer's 1961 result, precisely how much energy is dissipated when a single bit of neural information is erased. Not approximately, precisely. The universe did not give the father of information theory a professional courtesy exemption. It collected the same price from his brain that it collects from every glass bead in every laser trap in every laboratory on Earth. Shannon died on February 24, 2001. At the age of 84, he never received a Nobel Prize. There is no Nobel Prize category for what he did. He was too much of an engineer for the physics committee, too much of a mathematician for the engineering world, too fundamental for any single field to claim. The Nobel omission is worth dwelling on because it illustrates the same institutional blindness that kept his paper unread by physicists for decades. The Nobel Prize in Physics has been awarded for quantum mechanics, particle physics, cosmology, condensed matter, and optics. It has been awarded for the invention of the transistor, for the discovery of the cosmic microwave background, for the detection of gravitational waves. It has never been awarded for information theory. Not to Shannon, not to Landauer, not to anyone in the lineage of work that runs from Shannon's entropy through black holes and holography to the discovery that space-time is an error-correcting code. The committee has never recognized the most consequential intellectual trajectory of the past century. Shannon received the National Medal of Science in 1966, the Kyoto Prize in 1985, and the IEEE Medal of Honor. These are significant honors, but they are not the Nobel. And the absence of the Nobel sends a message about what the institutional gatekeepers of physics consider fundamental and what they consider merely applied. Shannon's work was neither. It was a mathematical truth about information that turned out to be a physical truth about reality, and the existing categories could not accommodate it. The most important scientist you have never heard of, who wrote the most important paper that physics never read, died in a nursing home having the most important equation in modern science demonstrated on his own neurons. But the story does not end with Shannon's death. It gets worse, because while Shannon was losing his memories in Medford, a generation of physicists was discovering that his equation did not just describe the thermodynamic cost of forgetting. It described something much stranger. It described the maximum information capacity of the universe. And the answer came from the most extreme objects in existence. In 1973, a 26-year-old graduate student at Princeton named Jacob Bekenstein published a paper that would eventually overturn the physics community's understanding of what space actually is. Bekenstein was working under John Archibald Wheeler, the man who had coined the phrase black hole, and who had been thinking more deeply than almost anyone alive about the relationship between information and physics. Wheeler was the kind of physicist who asked questions that his colleagues considered philosophical or even mystical, questions about the role of the observer, about whether physics is fundamentally about information, about whether the universe is, at bottom, built from yes or no questions. His most famous student, Richard Feynman, would win a Nobel Prize. His most disruptive student, Jacob Bekenstein, would change what we think reality is made of. Bekenstein had been born in Mexico City in 1947, the child of Jewish immigrants, and had moved to Israel as a teenager before coming to the United States for graduate study. He was quiet, persistent, and willing to follow a line of reasoning to conclusions that made everyone around him uncomfortable. Wheeler encouraged this quality. Wheeler had spent his career asking uncomfortable questions about the foundations of physics, and he recognized in Bekenstein a student who would not flinch when the math pointed somewhere strange. The reasoning that led to Bekenstein's proposal was disarmingly simple. The second law of thermodynamics says the total entropy of the universe cannot decrease. If you throw a cup of hot coffee into a black hole, the entropy of that coffee, the information about its molecular arrangement and temperature and composition, appears to vanish from the observable universe. If the black hole has no entropy of its own, then the total entropy of the universe has just decreased. The second law is violated. This bothered Bekenstein. It should have bothered more people than it did. The second law is not a suggestion. It is the most robust empirical generalization in all of physics. Eddington said, "If your theory disagrees with the second law, there is no hope for your theory." And here was a situation where general relativity, Einstein's crown jewel, appeared to create a mechanism for violating it. Bekenstein's solution was to give the black hole its own entropy, and not just any entropy, a specific, calculable amount. He proposed that the entropy of a black hole is proportional to the area of its event horizon, measured in Planck units. He published it in Physical Review D, Volume 7, Number 8, pages 2333 through 2346, April 15, 1973. The claim was radical, not just because it assigned thermodynamic properties to a gravitational object, but because of what it said about the geometry of information. If the entropy, the information content, of a black hole is proportional to its surface area rather than its volume, then information in the universe does not scale the way intuition suggests. You would expect that a bigger box can hold more information in proportion to its volume. Bekenstein was saying no. The maximum information you can pack into a region of space is set by the area of the boundary, not the volume enclosed. The universe has a built-in limit on information density, and that limit is a surface law, not a volume law. This was the first hint that the universe stores its information in a way that nobody expected, and it pointed toward a rethinking of what space itself actually is. Stephen Hawking did not believe this. He set out to prove Bekenstein wrong, and in 1974, he published a short paper in Nature, Volume 2, 48, pages 30 through 31, titled Black Hole Explosions, followed by the full treatment, Particle Creation by Black Holes, in Communications in Mathematical Physics, Volume 43, in 1975. What Hawking found stunned everyone, including himself. He demonstrated that black holes radiate. They have a temperature. They glow with thermal radiation, now called Hawking radiation, and the temperature is inversely proportional to their mass. The temperature of a solar mass black hole is about 60 billionths of a Kelvin, unimaginably cold, but not zero. To appreciate how profoundly disturbing this result was, you need to understand what physicists thought a black hole was. Before Hawking, it was a one-way door. Things fall in, nothing comes out. The event horizon is a boundary from which not even light can escape. This was not a feature of the theory. It was the definition. The defining characteristic of a black hole is that it has an event horizon. Hawking showed that the event horizon leaks, that quantum effects near the boundary cause the vacuum itself to radiate particles, slowly, imperceptibly, but relentlessly. The black hole has a temperature, and anything with a temperature radiates, and anything that radiates loses energy, and anything that loses energy loses mass. And a black hole that loses mass shrinks, and a black hole that shrinks gets hotter, and a hotter black hole radiates faster. And eventually, after a time span so incomprehensibly long that it makes the age of the universe look like a rounding error, the black hole evaporates completely. A solar mass black hole would take approximately 10 to the 67th years to evaporate. The universe is only about 10 to the 10th years old. We are not going to observe this process directly, but the mathematics is unambiguous. Black holes are temporary. Everything they swallow will eventually be returned to the universe as radiation. And here is where the crisis begins. The existence of this temperature forced Hawking to accept Bekenstein's entropy conjecture. But Hawking's calculation also fixed the proportionality constant that Bekenstein had left undetermined. The Bekenstein-Hawking entropy formula reads S equals K sub B times A divided by 4L sub P squared. S is the entropy. K sub B is Boltzmann's constant. A is the area of the event horizon. L sub P is the Planck length, 1.616 times 10 to the minus 35 meters, the smallest meaningful length scale in physics. The factor of 1/4 was Hawking's contribution. Bekenstein had argued the entropy was proportional to the area. Hawking pinned down the coefficient. The numbers are staggering. A black hole with the mass of our sun has an event horizon area of roughly 7 times 10 to the 7th square meters, about the area of a large city. Its Bekenstein-Hawking entropy is approximately 10 to the 77th Boltzmann units. The sun's own thermodynamic entropy, the entropy of a ball of hydrogen plasma, 1.4 million kilometers in diameter, burning at 15 million degrees, is roughly 10 to the 58th Boltzmann units. The black hole carries 1 billion trillion times more entropy than the star it was made from. Black holes are, by an obscene margin, the densest information storage systems permitted by physics. And all of that information is encoded on the 2-dimensional surface, not in the 3-dimensional interior. This result should have been treated as one of the most important discoveries in the history of physics. It was the first concrete link between gravity, quantum mechanics, and information theory. It showed that Shannon's concept of entropy, the same entropy he had defined in a telephone journal, applied to the most extreme gravitational objects in the universe. It showed that the information capacity of space has a fundamentally geometric character tied to surfaces rather than volumes. And it pointed toward a reconceptualization of space itself, a possibility so strange that it took another 20 years for anyone to fully articulate it. But Hawking's result also created a catastrophe. If black holes radiate, and the radiation is perfectly thermal, then the radiation carries no information about what fell in. It is random, featureless. When the black hole finally evaporates completely, after an unimaginable span of time, all the information it stored appears to be gone, destroyed, not just scattered or scrambled, but actually removed from the universe. And the universe does not allow that. Quantum mechanics is a unitary theory. Its fundamental equations are reversible. If you know the complete quantum state of a system, At one moment, you can in principle determine its state at any other moment, past or future. Information is conserved. You can shuffle it around, hide it in correlations, spread it across billions of particles, but you cannot reduce the total amount. Destroying information breaks unitarity. It breaks the time reversibility of quantum mechanics. It breaks the mathematical framework that every other prediction in physics is built on. Hawking was claiming, based on rigorous calculation, that black holes break quantum mechanics. He published this explicitly in 1976 in a paper titled Breakdown of Predictability in Gravitational Collapse in Physical Review D. He was saying that the universe can forget, that information can be permanently erased. And if that is true, then either quantum mechanics is wrong, or general relativity is wrong, or something about the way they interact is fundamentally misunderstood. This became the black hole information paradox. It divided theoretical physics for decades. It was not a polite disagreement about interpretation. It was a crisis at the foundation of the subject. If information can be destroyed, quantum mechanics, as we know it, is wrong. If information must be preserved, then Hawking's calculation of radiation temperature, one of the most celebrated results in modern physics, is incomplete in a way that nobody could identify. The stakes were not academic. Quantum mechanics underlies every piece of technology you use. Semiconductors, lasers, MRI machines, nuclear energy, the GPS satellites that guide your phone. All of them work because quantum mechanics makes precise, testable predictions that have been confirmed to extraordinary accuracy. The quantum electrodynamic prediction of the electron's anomalous magnetic moment agrees with experiment to better than 10 parts per billion. It is the most precisely tested prediction in the history of science. And Hawking was saying that the framework that produces this prediction breaks down in the presence of strong gravity. That unitarity, the mathematical property that guarantees information conservation and that makes quantum mechanics a predictive theory, fails when a black hole is involved. If Hawking was right, the implications extended far beyond black holes. If unitarity can be violated in one situation, the entire logical structure of quantum mechanics is called into question. The precision tests that confirm quantum theory would be standing on an unstable foundation. The whole edifice might be approximate rather than exact, valid in most situations, but failing in extreme ones. And if it fails in extreme situations, you lose the ability to make sharp predictions about any situation, because you can never be sure that the conditions of your experiment are not, in some subtle way, extreme enough to trigger the failure. This is why the information paradox consumed so much effort. It was not a puzzle about exotic objects in distant space. It was a question about whether the fundamental framework of physics is consistent, whether the laws of nature, as we understand them, are compatible with each other, whether reality makes sense. The formal bet between Hawking, Thorne, and Preskill, made in 1997, crystallized the stakes. Hawking and Thorne bet that information is destroyed in black hole evaporation. Preskill bet that it is preserved. The stakes were an encyclopedia of the winner's choice. This was itself an information theoretic joke, one that all three men appreciated. The bet was about whether the universe preserves information. The prize was a physical repository of information. The concession came 7 years later, on July 21st, 2004, at the 17th International Conference on General Relativity and Gravitation in Dublin, Ireland. Hawking had requested a special session. The room was packed. He had been the most famous physicist in the world since the publication of A Brief History of Time in 1988. And word had spread that he was going to reverse one of his most famous positions. He arrived in his wheelchair, the speech synthesizer mounted on the armrest, and delivered a talk arguing that the information does escape, that the correlations in the Hawking radiation are subtle but real, and that quantum mechanics is correct after all. He presented Preskill with a copy of Total Baseball, the ultimate baseball encyclopedia, calling it the easiest encyclopedia to find in America, and joked that perhaps he should have given Preskill the ashes of the book to better symbolize the converted information from the black hole. Preskill, for his part, said he was still not entirely satisfied with Hawking's argument and would need to study it further. Kip Thorne refused to concede and has maintained his position ever since, arguing that the question is not yet settled. What made the concession significant was not the change of one man's opinion. It was the shift it represented in the physics community's center of gravity. By 2004, the preponderance of evidence from AD//CFT, from string theory calculations, from multiple independent lines of argument, pointed toward information conservation. Hawking's concession ratified what most theorists already believed. The universe remembers. The question was no longer whether information survives. The question was how. But Hawking's concession, important as it was symbolically, did not solve the technical problem. How does the information get out? The radiation looks thermal. Where are the correlations hiding? What mechanism preserves unitarity while still producing radiation that looks random to any local observer? The answer emerged over the following decade and a half, and every piece of it connects back to Shannon. Gerard Hooft proposed the holographic principle in 1993. Susskind formalized it in 1995. The principle generalizes Bekenstein's area scaling result to all of space. The maximum information in any region is proportional to its boundary area in Planck units, not its volume. This means the three-dimensional space you perceive around you has an information capacity that is fundamentally two-dimensional. The deepest description of reality is written on surfaces, not in volumes. The universe is a hologram, not in the science fiction sense of a flickering projection, but in the mathematical sense that the complete description of a three-dimensional region is encoded in data on a two-dimensional boundary, with no loss of information. Think about how strange this is. You are sitting in a room. The room has a volume. You would naturally assume that the amount of stuff that can happen in the room, the amount of information it can contain, scales with the volume. Twice the room, twice the information capacity. That is wrong. The maximum information the room can contain scales with the area of its walls. If the room is 10 meters on a side, the volume is 1,000 cubic meters, but the information capacity is determined by 600 square meters of wall surface. And the information limit is not some astronomical number far beyond practical relevance. It is exactly A divided by 4L sub P squared, where A is the surface area and L sub P is the Planck length. For a 10-meter room, that works out to roughly 10 to the 70 bits. That sounds like a lot, and it is, but it is not infinite, and it is determined by the surface, not the volume. Your room has a maximum information capacity, and that capacity is written on its walls. This result forced a reconceptualization of what space actually is. If the information content of a region is encoded on its boundary, then the three-dimensional interior is in some sense redundant. The boundary contains everything. The interior is a reconstruction, a projection, an emergent structure that unfolds from boundary data, the the way a hologram unfolds from a two-dimensional pattern etched in film. Space, the thing you move through, the thing you take for granted as the container of all physical experience, may not be fundamental. It may be derived. It may be what information looks like from the inside. John Wheeler had been waiting for this moment for decades. He had sensed the connection between information and physics long before the holographic principle was articulated, long before Bekenstein's paper, long before anyone had the mathematical tools to make the intuition precise. Wheeler had spent the post-war decades migrating from nuclear physics to general relativity to quantum gravity to the foundations of quantum mechanics, each move taking him deeper into the question of what physics is actually about. And by the late 1970s, he had arrived at a conviction that his colleagues found somewhere between visionary and deranged. At a conference at the Santa Fe Institute in 1989, and then formally in a paper published in 1990, in the proceedings of the Third International Symposium on Foundations of Quantum Mechanics in Tokyo, Wheeler articulated his position in 3 words: it from bit. His full statement reads, and I am paraphrasing, to respect the original while giving you the substance. It from bit symbolizes the idea that every item of the physical world has at bottom an immaterial source and explanation, that what we call reality arises in the last analysis from the posing of yes-no questions and the registering of equipment-evoked responses. In short, that all things physical are information theoretic, in origin, and this is a participatory universe. Wheeler was 78 when he published that. He had mentored Feynman and Bekenstein. He had worked on the Manhattan Project. He had co-authored the definitive textbook on general relativity with Kip Thorne and Charles Misner. He was one of the most respected living physicists, and he was telling the world that Shannon's bit, the binary digit, the unit of information defined in a footnote of a telephone company journal in 1948, is the fundamental unit of physical reality. Not the atom, not the quark, not the string, the bit. Wheeler died in 2008 at the age of 96. Bekenstein, his disruptive graduate student, died in August of 2015, just months after the Almhiri-Dom Harlow paper confirmed that space-time operates as an error-correcting code within the holographic framework. Bekenstein did not live to see the full resolution of the paradox his own work had helped create, but he lived long enough to see the direction, to see that his 1973 intuition, that black holes store information on their surfaces, and that this fact reveals something fundamental about the nature of space, had been vindicated far beyond what he had originally imagined. Juan Maldacena's 1997 ads/CFT correspondence made this concrete. He showed that a theory of quantum gravity in a specific curved space-time called anti-de Sitter space is exactly equivalent to a quantum field theory without gravity living on its boundary. The boundary theory contains all the information, the bulk geometry, the three-dimensional interior with its curves, and its gravity, and its space-time emerges from the boundary data. Space is not fundamental. It is derived. It is what information looks like when you view it from the inside. Maldacena's paper, published in the same year that the Thorne-Hawking-Preskill bet was formalized, has been cited over 20,000 times. It is the most cited paper in the history of high-energy physics, and it says, in the language of mathematics, exactly what Wheeler said in the language of philosophy. It from bit. Reality is information. Eric Verlinde at the University of Amsterdam pushed this further in 2011, publishing a paper in the Journal of High Energy Physics titled On the Origin of Gravity and the Laws of Newton. Verlinde argued that gravity itself is not a fundamental force. It is an entropic effect, a statistical tendency arising from changes in information on holographic screens. His proposal derives Newton's law of gravitation and Einstein's equations of general relativity from thermodynamic reasoning and the holographic principle. The reaction from the physics community was, characteristically, divided. Andrew Strominger of Harvard summarized it by saying some people have said it cannot be right, others that it is right and we already knew it, and still others that it is right and profound. Experimental tests using dwarf galaxy rotation curves, published by Chris Pardo at Princeton in 2017, found that Valinda's predictions underperform in certain regimes. The theory is not settled, but the direction is unmistakable. Even gravity, the force that holds you to the Earth, may be an informational phenomenon, a consequence of entropy, a downstream effect of Shannon's equation. Then came ER equals EPR. In 2013, Maldacena and Susskind connected two results from 1935. Einstein-Rosen bridges, wormholes in spacetime, are the same thing as Einstein-Podolsky-Rosen entanglement, quantum correlations between distant particles. Two entangled particles are connected by a microscopic wormhole. The wormhole is not traversable, not useful for communication, but it is a geometric connection. Space-time connectivity, the thing that makes space hang together as a continuous fabric rather than flying apart into disconnected chunks, is woven from entanglement. From quantum information, the stitching that holds the universe together is made of bits. I want you to understand how radical this claim is, because it tends to get lost in the jargon. When you look across a room, you perceive a continuous space between you and the far wall. There are no gaps, no disconnections, no places where space simply stops existing. Space is smooth and connected. You take this for granted. Everybody does. It seems like the most basic property a container could have. Maldacena and Susskind are saying that this connectivity, this smoothness, this seamless quality of space exists because of quantum entanglement, because the quantum degrees of freedom in different regions of space are correlated with each other. If you could somehow remove all the entanglement, if you could disentangle the quantum fields in one region from the quantum fields in another, the space between them would not just become empty. It would cease to exist. The regions would become geometrically disconnected, separate universes. Space in this picture is not a stage on which quantum entanglement occurs. Space is what quantum entanglement looks like when you zoom out far enough. The geometry is the entanglement. Mark van Ramstonk at the University of British Columbia made this vivid in a 2010 paper published in General Relativity and Gravitation. He showed, within the ADS/CFT framework, that reducing the entanglement between two halves of a boundary theory causes the corresponding bulk spacetime to pinch off and disconnect. He titled the paper, "Building Up Spacetime with Quantum Entanglement." The image he offered was this. Imagine the boundary theory as a sheet of rubber. Entanglement between different parts of the sheet is what gives the corresponding space-time its geometry, its shape, its connectedness. Cut the entanglement, and the space-time tears. The interior geometry responds to changes in boundary entanglement the way a puppet responds to its strings, except the strings are quantum correlations, and the puppet is the fabric of reality. This was the context for the final result, the one that ties everything in this story into a single knot. And finally, in 2015, Ahmed Almhiri, Shidong, and Daniel Harlow published a paper showing that the ADS/CFT dictionary, the mathematical mapping between boundary information and bulk space-time, has the structure of a quantum error-correcting code. The information describing a point in the interior of spacetime is not stored at any single location on the boundary. It is encoded redundantly across many boundary degrees of freedom, distributed in exactly the way that would protect it from local erasure. If you destroy a small portion of the boundary, the interior information can still be reconstructed from what remains. The universe encodes its own geometry with redundancy, with error correction, with the same mathematical strategy Shannon proved must exist in 1948 for reliable communication through a noisy channel. John Preskill called it what it is. Space-time is a quantum error-correcting code. The subsequent work has only strengthened this picture. Fernando Pastowski, Benny Yoshida, Daniel Harlow, and John Preskill published a paper in 2015 constructing an explicit toy model of how holographic error correction works. They called it the Happy Code after the initials of its authors, and it showed how a simple tensor network, a mathematical structure built from interlocking blocks of quantum information, could reproduce the key features of the ADS/CFT dictionary. The interior geometry of spacetime emerges from the entanglement structure of the network. The error-correcting properties arise naturally. The model is simple enough to compute with and deep enough to capture the essential physics. It was a proof of concept. The universe's error-correcting code might be vastly more complex than the Happy model, but the Happy model showed that the idea works, that the connection between Shannon's coding theorems and the structure of space-time is not just an analogy, it is a constructive, mathematical fact. In 2019, the information paradox itself began to crack open. Jeffrey Pennington at Stanford, and independently the team of Ahmed Almhiri, Netta Engelhardt, Donald Marolf, and Henry Maxfield published papers deriving what physicists call the Page curve. Don Page had argued in 1993 that if black hole evaporation is unitary, if information is truly preserved, then the entanglement entropy of the Hawking radiation must follow a specific curve. It must rise as the black hole emits radiation, peak at the halfway point of evaporation, and then fall back to zero as the last of the information escapes. This curve had been the holy grail of black hole physics for 26 years. Nobody could derive it from first principles. Pennington and the AEMM team did. Using techniques that grew directly out of the holographic error correction framework, they showed that new geometric contributions to the gravitational path integral, called quantum extremal surfaces and islands, reproduce the Page curve exactly. The information does get out. It gets out through the same entanglement structure that holds space-time together. The error-correcting code does its job. The information paradox, the problem that consumed theoretical physics for 43 years, appears to be resolvable precisely because space-time operates according to Shannon's coding principles. I want to say that again because it deserves to be said clearly. The 40-year crisis in theoretical physics, the question of whether black holes destroy information, appears to have been resolved by the recognition that space-time is an error-correcting code. Shannon's 1948 theorem about how to send reliable messages through a noisy channel turned out to be the key to understanding what happens when a star collapses into a black hole and evaporates. Over trillions of years, the telephone theorem solved the black hole problem. That sentence should not make sense. And yet, here we are. I need to be precise about what is proven and what is conjectured, because this audience deserves precision, and I intend to provide it. The Almhiri-Dom-Harlow result is a mathematical theorem within the ADS/CFT framework. The ADS/CFT correspondence itself is the most well-tested and widely accepted conjecture in theoretical physics, supported by thousands of papers and consistency checks, but it has not been directly experimentally verified. Our universe is not an anti-de Sitter space, and extending the holographic results from ADES to the de Sitter spacetime we actually live in is an active, difficult, unresolved problem. ER equals EPR is a conjecture. The holographic principle, in its full generality, is a conjecture. But the trajectory is clear and the confirmed foundations are unshakable. Shannon entropy is identical to Boltzmann entropy, and this is not a coincidence. Information is physical, confirmed by laboratory experiment. Black hole entropy is a surface quantity, derivable from first principles. The holographic bound on information follows directly, and within the mathematical models that physicists actually use to make calculations, the error-correcting structure is a derived result. Every decade since 1948 has revealed Shannon's paper to be about something deeper than anyone understood. Communication, then thermodynamics, then black holes, then the geometry of space and time. Each layer makes the previous one look like surface skimming, and nobody is willing to assert that we have reached the bottom. I want to return one last time to the nursing home in Medford, Massachusetts. I want to return to Claude Shannon in the late 1990s, sitting in a room he does not recognize, surrounded by staff whose names he cannot retain. His mind progressively losing the very information his life's work proved is physical and consequential and thermodynamically real. I have been thinking about what it must have been like for him in those final years, and I realize that thinking about it is itself an exercise in the physics he discovered, because my thoughts about Shannon are information. They are encoded in my neurons. They will persist for as long as my synapses hold them, and then they will dissipate. And the dissipation will generate heat, and the heat will carry the remnant of the thought into the environment. This is not philosophy. This is thermodynamics. Shannon in that nursing home was a man being slowly converted from a signal into noise. The signal was extraordinary. The most important insights of the 20th century were encoded in his neural architecture. The bridge between logic and circuits. The bridge between information and entropy. The mathematical foundations of the digital world. The accidental description of the operating system of reality. All stored in electrochemical patterns in roughly 1.4 kilograms of tissue. And Alzheimer's disease was erasing those patterns, one synaptic connection at a time, converting structured information into thermal disorder. His brain was undergoing exactly the process his own equation describes. It was losing information, and the universe was collecting the Landauer tax on every bit. Betty Shannon came to see him. She came regularly. She had spent 50 years with this man. She had been his collaborator, his proofreader, his partner in the experiments that quantified the redundancy of English by having human subjects guess the next letter in a text, one character at a time, measuring how much of the language is actually informative and how much is predictable structure. She had co-authored work with him on the maze-solving mouse Theseus, an electromechanical mouse that could learn and remember a maze, one of the first demonstrations of machine learning. She had been with him on the Vegas trip with the wearable computer. She had lived in Entropy House, the sprawling residence in Winchester, Massachusetts, filled with his gadgets and inventions and toys. She had watched him invest in the stock market, using information theoretic principles, and compound his wealth for decades. She had raised Robert, Andrew, and Margarita in a house that was equal parts laboratory and playground, where their father would demonstrate mathematical principles with juggling balls and prove theorems about unicycling at the dinner table. And now she sat with a man who could not remember any of it. There is something about Alzheimer's disease that makes it uniquely relevant to Shannon's work, and I do not think this connection has been adequately explored. Alzheimer's is not just a disease that damages the brain. It is a disease that destroys information, specifically and progressively. It attacks the hippocampus first, the brain region most directly responsible for converting short-term memories into long-term storage. Then it spreads to the cortex, degrading stored memories, eroding language, dissolving personality. It is, from an information theoretic perspective, a systematic increase in entropy within a neural information system. The channel is degrading. The noise is overwhelming the signal. The error correction capacity of the brain's own redundant encoding is being exceeded, and the information is being lost. But lost to where? This is the question that Shannon's own work forces you to ask, and the answer is the thread that ties this entire story into a single knot. Because here is what connects everything. Information is physical. The erasure of information costs energy. The universe enforces this at every scale, from glass beads in laser traps to black holes evaporating over trillions of years. And the universe does not allow the total destruction of information. Quantum mechanics is unitary. The equations run both ways. Information can be scrambled, dispersed, entangled with the environment, diluted until no physical process could ever reassemble it. But it cannot be subtracted from the total. The ledger must balance. This is not a gentle philosophical observation. It is a mathematical constraint imposed by the fundamental equations of physics. The Schrödinger equation is unitary. The S-matrix of quantum field theory is unitary. The ADS/CFT dictionary preserves information exactly. At every level of physical theory, from the most basic quantum mechanics to the most sophisticated models of quantum gravity, the conservation of information is built into the formalism. It is as non-negotiable as the conservation of energy. It is, in some formulations, more fundamental. The information that was Claude Shannon, the specific configuration of neural states that stored his memory of riding a unicycle through Bell Labs while tossing balls in the air, his memory of the moment he realized Boolean algebra mapped onto relay circuits, his memory of sitting across from Alan Turing in a cafeteria in the winter of 1943 discussing whether machines could think, while neither of them could discuss what they were actually working on. His memory of the moment he saw that his entropy formula matched Boltzmann's and asked von Neumann what to call it. His memory of the evening in Vegas when the speaker wire broke and the wearable computer went silent against his ankle. His memory of Betty's face when she found the proof of the channel coding theorem scrawled on a notepad and asked if he understood what he had just done. All of that information was not destroyed when his neurons degraded. It was dispersed, scattered into thermal radiation, into molecular vibrations, into the quantum state of the air and the walls and the floor and the bodies of the nurses who cared for him and the visitors who came and went, into the infrared photons that escaped through the windows of the nursing home and propagated outward at the speed of light, into the gravitational waves generated by the redistribution of mass as his body shifted in a chair, into correlations and entanglements so deep and so dispersed across so many degrees of freedom that no instrument, no computer, no technology conceivable within the laws of physics could ever disentangle them. But not gone. The laws of physics do not permit it to be gone. The same principles that Shannon helped discover, that Landauer made thermodynamically precise, that Bekenstein and Hawking found governing black holes, that Hooft and Susskind and Maldacena found written into the holographic structure of spacetime. that Almehiri and Dong and Harlow found operating as an error-correcting code at the deepest level of the geometry of reality, those principles apply to every bit of information in the universe without exception. The exception was never available. It was never on the table. The universe does not negotiate, it does not grant exemptions for famous physicists or for the fathers of information theory, or for anyone else. The information is conserved. Period. The father of information became information. Scattered across the quantum state of the observable universe in correlations too fine to ever measure, irretrievable by any conceivable physical process, but present, persistent, conserved, exactly as his theory predicts. And this applies to you. Right now, as you are hearing this, the information that constitutes your identity, your memories, your habits, your sense of humor, the particular way you hold a cup or recognize a friend's voice across a crowded room, is encoded in the physical states of your neurons. It is subject to every principle described in this story. It is Shannon measurable, Landauer taxed, Bekenstein bounded, holographically encoded on the boundary of whatever region of spacetime you currently occupy. The universe is tracking every bit. The universe has been tracking every bit since the moment the first bit came into existence. And the universe will not, cannot, under any formulation of the laws of physics that we currently possess, allow the total to decrease. What happens to you when you die is, from an information theoretic standpoint, exactly what happened to Claude Shannon when his neurons degraded. The information that constitutes you will be dispersed, scattered into the thermal and quantum environment, distributed across correlations so vast and so entangled that they are functionally indistinguishable from noise. You will become, in the language of information theory, a signal so thoroughly scrambled that it cannot be distinguished from the noise of the universe, functionally erased. But functionally erased and actually erased are two different things, and the difference between them is not a loophole or a technicality. It is the most important distinction in all of physics. It is the distinction that drives the black hole information paradox. It is the distinction that led to the holographic principle. It is the distinction that motivated ER equals EPR and the discovery that spacetime is an error-correcting code. The entire trajectory of the last 50 years of theoretical physics has been driven by the insistence that this distinction matters. That information scrambled is not the same as information destroyed, and that the universe takes this distinction seriously even when humans do not. Shannon did not know any of this when he sat in his office at Bell Labs, 463 West Street in Manhattan, and worked out the entropy formula on a pad of paper. He thought he was playing with a communications problem, a pretty puzzle. He thought it was, in his own characteristically humble words, totally useless. He published it in a corporate journal because that is where Bell Labs employees published. He watched the physics community ignore it for decades. He warned them in a one-page editorial that they were looking in the wrong places and ignoring the right ones. They ignored the warning too. He spent his final decade in a nursing home, unaware that the equation he had written as a 32-year-old had turned out to describe the deepest architecture of reality that human beings have ever uncovered. Unaware that the word bit, which his friend Tukey had coined in a memo, had become one of the defining concepts of human civilization. Unaware that his noisy channel coding theorem, his elegant proof that error-correcting codes must exist, had turned out to describe the mechanism by which the universe maintains its own structural integrity. Unaware that his entropy formula, the one von Neumann jokingly said to name after thermodynamic entropy because nobody understands it, had turned out to be thermodynamic entropy. Not an analogy, not a metaphor. The same quantity, measuring the same thing. Because information is what the universe is made of. The paper is still there. It has never moved. 79 pages. Volume 27 of the Bell System Technical Journal. July and October 1948. A mathematical theory of communication, with the indefinite article, because Shannon was modest, with the word bit in a footnote, because Tukey was casual, with the entropy formula on page 11, because von Neumann had a sense of humor. The most important paper nobody read. Nearly 80 years later, physics is still discovering what it means. Every decade peels back another layer. Communication, thermodynamics, computation, black holes, space-time, error correction. The trajectory has not flattened. It has not reached a final depth. And the pattern that has held for 80 years, the pattern where each new generation of physicists finds that Shannon's paper describes something deeper and more fundamental than the previous generation realized, shows no sign of breaking. I do not know what the next layer will be. Nobody does. But if the pattern holds, it will be something that makes everything I have described in the last 2 hours look like surface scratching. Shannon's paper has been doing this for 8 decades. It has been sitting there in a telephone journal, 79 pages of mathematics, and every time someone reads it carefully and takes it seriously, they find that it describes more of reality than anyone thought possible. You are made of bits. The universe is keeping count, and it will never, under any circumstance, let the total go down.